Welcome to Short Planetary Geological Essays, narrated by Daniel Hutchinson. Planetary Geology Essay, The Planet Mercury. The geology of Mercury is the scientific study of the surface, crust, and interior of the planet. It emphasizes the composition, structure, history, and physical processes that shape the planet. It is analogous to the field of terrestrial geology. In planetary science, the term geology is used in its broadest sense to mean the study of the solid parts of planets and moons. The term incorporates aspects of geophysics, geochemistry, mineralogy, geodesy, and cartography. Astronomically speaking, Mercury has been the least understood of all the terrestrial planets in our solar system. This stems largely from its proximity to the Sun, which makes reaching it with spacecraft a technical challenge, with Earth-based observations difficult. For decades, the principal source of geological information about Mercury came from the 2,700 images taken by the Mariner 10 spacecraft during its 3 flybys of the planet from 1974 to 1975. Images obtained at the time covered only about 45% of the planet's surface. Many of the images were unsuitable for any amount of a detailed geological investigation, based on high sun angles, making it difficult to determine the planet's surface morphology and topography. The next space probe launched at Mercury, the Messenger space probe, between 2008 and 2015, collected over 291,000 images, covering the entire planet, along with a wealth of other scientific data. The European Space Agency's Bepi-Colombo space probe is scheduled to go into orbit around Mercury in 2025. It is expected to help answer many of the remaining questions about Mercury's geology. Mercury's surface is dominated by impact craters, with basaltic rock and smooth plains. Many of the plains are a result of flood volcanism, similar in some respects to the maria on the surface of the Moon. Other notable features include vents, which appear to be the source of magma-carved valleys, often grouped irregular-shaped depressions termed hollows that are believed to be the result of collapsed magma chambers, and scarps indicative of thrust faulting. Mercury has a solid iron-rich core, that which accounts for about 60% of its volume and 75% of its radius. As mentioned, reaching Mercury from Earth poses significant technical challenges. Because the planet orbits so much closer to the Sun than does the Earth, the space environment near Mercury is demanding, posing the double dangers to spacecraft of intense solar radiation and high temperatures. Historically, another obstacle has been that Mercury's period of rotation is a slow 58 Earth days, so that spacecraft flybys are restricted to viewing only a single illuminated hemisphere. Like the Earth, Moon, and Mars, Mercury's geological history is divided up into eras, from oldest to youngest. These are the pre-Tolstoyan, Silurian, Mansurian, and Kuiperian ages. These ages are based on relative dating only. After the formation of Mercury along with the rest of the solar system 4.6 billion years ago, heavy bombardment by asteroids and comets ensued. The last intense bombardment phase, the late heavy bombardment, came to an end about 3.8 billion years ago. Some regions, or massifs, a prominent one being the one that formed the Caloris Basin, were filled by magma eruptions from within the planet. These created smooth intercrater plains similar to the maria found on the Moon. Later, as the planet cooled and contracted, its surface began to crack and form ridges. These surface cracks and ridges can be seen on top of the other features such as the craters and smoother plains, a clear indication that they are more recent. Mercury's period of volcanism ended when the planet's mantle had contracted enough to prevent further lava from breaking through the surface. This probably occurred at some point during its first 700 or 800 million years of history. Since then, the main surface processes have been intermittent impacts. Mercury's Caloris Basin is one of the largest impact features in the solar system. Shock waves generated during this massive impact traveled around the planet and then converged at the basin's antipode, 180 degrees away. The high stresses were capable of fracturing the surface. Smaller than this largest of features on the planet's surface are the craters of Mercury that range in diameter from small bowl-shaped craters to multi-ring impact basins hundreds of miles across. They appear in all states of degradation, from relatively fresh rayed craters to highly degraded crater remnants. Mercurian craters differ subtly from lunar craters. The extent of their ejecta blankets is much smaller, which is a consequence of the 2.5 times stronger surface gravity on the planet. Mercury's surface is also flexed by significant tidal bulges raised by the Sun. The Sun's tides on Mercury are about 17% stronger than the Moon's on Earth. In spite of its proximity to the Sun, Mercury may have surface ice, since temperatures near the poles are constantly below the freezing point. On the polar plains of Mercury, the temperature does not rise above minus 223 degrees Fahrenheit, and craters at Mercury's higher latitudes may be deep enough to shield the ice from direct sunlight. Inside the craters, where there is no solar light, temperatures fall to minus 340 degrees Fahrenheit. Despite sublimation into the vacuum of space, the temperature in the permanently shadowed region is so low that this sublimation is slow enough to potentially preserve deposited ice for billions of years. Mercury is not unique in having craters that stand in permanent shadow. At the south pole of Earth's moon, there is a large crater called Atkin, where some possible signs of lunar ice have been seen. Astronomers think that ice on both Mercury and the moon must have originated from external sources, most likely that of impacting comets. These are known to contain large amounts of ice. It is therefore possible for cometary impacts to have deposited water in the permanent shadowed craters, remaining unwarmed for possibly billions of years, due to the lack of an atmosphere on Mercury to efficiently conduct heat, and also Mercury's lack of a stable orientation of the planet's rotational axis. Finally, there may be scientific support based on studies reported in March of 2020 that parts of the planet Mercury may have been inhabited by primitive microorganisms existing at some point in time in the planet's distant past. Thank you for watching, and I hope you have enjoyed this video about the geology of the planet Mercury.